Good morning, all the participants. Welcome to the lecture 8, topic name Alternative Fuels 1 Scopes, Types, and State of the Art. I welcome Professor Ian Wenming from NUS Singapore to deliver this lecture. Over to you, sir.
Okay, thank you. Okay, yeah, so start from this class, we're going to introduce alternative fuel. First one, I want to introduce, first one I want to introduce is the biofuel landscape and the cost for the various biofuel. For example, so first one is the Brent crude oil. The price is roughly about 415 to 449 US dollars per ton. And the diesel fuel, the price is about 1,045 to 1,112 US dollars per ton. And the POD, by massive production, the price is about 1,100 to 1,300 US dollars per ton. And the AME, the price is from 914 to 1,370. And the SME, the price is 799 to 952. Rapeseed oil is about 800 to 900. And palm oil is cheaper. It's 476 to 691. So ethanol is even cheaper. So here we show you the market landscape and the price to produce a various biofuel and active fuel. So for this investigation, firstly, we have built 2 engine testbed in our lab. So first one is a single cylinder engine testbed. This one, actually the control system, the ECU was designed by ourselves. So by using the built-in house ECU, we can change the course of injection amount, fuel injection timing. We can change the fuel injection strategy. For example, we can use multiple injections. And this one is a 4-cylinder engines. Also is a diesel engine, and again also can change the ECU as well for better experimental tests. So for these 2 engine tests, actually we can test a conventional fuel, for example, diesel fuel, jet fuel, and also can test surrogate fuels like biofuel, POD, and any future fuels. And the emissions we can measure is the CO NOx emission and unburned HC and the CO2 emissions. The engine parameters we can change the engine. The engine speed, the engine node, engine torque or engine loader. Also have built a small setup to produce biodiesel. This one is actually quite simple one. We can produce biodiesel 0.5 kilograms each time by using this a small setup. So here actually use we use the vegetable oil together with methanol and some catalyst QOH. Then we can change the vegetable oil into biodiesel and glycerin. So from this graph, actually you can see the top one. The top one is biodiesel, and the bottom one is the water and glycerin. Water and glycerin. So the best optimum operating temperature for this reaction is 60 to 80 degrees C. So I have produced biodiesels from different edible feedstocks. For example, produce the biodiesel from coal oil, and produce biodiesel from sunflower oil and canola oil, palm tree, the palm oil, soybean oil. So here we show the biodiesel produced by from various feedstocks. Okay, so first one is the biodiesel produced by with cooking oil. So you can see the color is deeper than the rest, correct? Because the with cooking oil actually is dirty, it's dirty and so color is deeper. Okay, in addition to the edible feedstocks, also we can produce biodiesel from non-edible feedstocks. For example, can produce biodiesel from kapa seeds. Okay, so here's the biodiesel produced by the kapa seeds. And also had tried to produce biodiesel from cashew nut shell. Okay, usually this cashew nut shell was discarded as a waste, but in this cashew nut shell actually contains about 30% of cashew nut liquid, nut shell liquid. Okay, so this one is produced by hot pressing this cashew nut shell. So use steam and use a high pressure to compress the cashew nut shell. Then we can produce cashew nut shell liquid. Then further use the method just I introduced, okay, to change the cashew nut shell liquid into biodiesel. Okay, so next one is the next one is the biodiesel produced from non-edible feedstocks. For example, the pantry gum. From this pantry gum, we can produce palm oil. Okay, this palm oil actually we don't need to convert into biodiesel. We don't need to further convert into biodiesel because the palm oil actually the property is quite similar to the diesel fuel, Also, no need to further decompose the palm oil into smaller molecules we can directly use in the engines. So next one is mahua seeds. From the mahua seeds, we can produce mahua oil biodiesel. Okay, so here shows the biodiesel produced from this mahua seeds. Okay, so after produce the biodiesel from various feedstocks, then we analyze the major compositions. We notice that all the biodiesel contains these 5 major components, namely methyl palmitate, methyl stearate, methyl oleate, methyl nanoate, and methyl nanolinate. Okay, so here shows the formulas for the various major components and also the percentage of different composition. So you can see if compare soybean, rapeseed, and palm biodiesel. So you can see the major components. Okay, the percentage is different. Okay, for the different feedstock. For example, in this palm biodiesel, okay, this one has the biggest percentage. Okay, this kind of composition has the biggest percentage. The second biggest one is this one, 43.4. Okay, this one. And for rapeseed biodiesel, okay, this composition has the highest percentage. And for soybean biodiesel, okay, this composition has the highest percentage. Okay, so the biodiesel produced from different feedstock, the major compositions, the percentage will be changed, will be different. Okay. Okay, so here we show you the chemical formulas and the molecular weight as well as the number of atoms. Here we show you the molecular structure. Okay, so for the first one, okay, for the first composition, as you can see, this molecule is a straight like carbon chain, correct? Straight like carbon chains. And for the second one, okay, that's no double bond. For the second one is C19H30AO2. Again, this one is also a straight like carbon chains and there's no double bond. But the carbons, we have 90 carbons. And this one has only 70 carbons. And the third composition methyl onate, okay, has one double bond here. Okay, this one is a double bond. So this composition has one double bond. And this one, methyl nonate, has a two double bond, 1 and 2. Okay, has two double bond. And the composition, okay, so sorry, the fifth composition has three double bond. Okay, 1, 2, and 3, three double bond. Okay, so can see actually this is five major components. So in terms of atoms, number of atoms will be different. And in terms of molecular structure, okay, some of the compositions has double bond, some of them don't have double bond, correct? In the previous lectures, we introduced the double bond has a big impact on the physical chemical properties of the fuel and also on the emissions, correct? Basically, the double bond will increase the soot emissions, because double bond is more stronger and not easier to break, so tend to produce more soot emissions. Okay, so here we show you some the properties of some biofuel, biodiesel. Okay, this one pan oil. Okay, the density is about 0.875, and copper ester is 0.875, is similar, but the cashew nut shell, liquid biodiesel, the density is higher. Okay, so also combines viscosity. Pan oil is 1.3, actually it's even lesser than the diesel fuel, correct? So diesel fuel, the viscosity is 2.17, correct? And the copper ester is greater than diesel fuel. And the cashew nut shell has the highest viscosity, okay? Has the highest viscosity. This actually the viscosity will affect the fuel atomization and affects the fuel evaporation. Okay. Here show you the flash point for the pan oil is 52 degrees C, and copper oil is 170 degree, and the cashew nut shell is 148. So the boiling temperature is also different for the different biodiesel. And the heating value also quite different. Pan oil has the highest heating value. Okay, actually this value is very close to the diesel fuel. Okay, close to the diesel fuel heating value is similar. And copper ester, the heating value is only 36, and cashew nut shell, liquid biodiesel, is even smaller. And the sulfur content pan oil is less than 0.005%. Okay, the cashew nut shell is higher, okay, but still less than 0.05. Okay, so the C10 number, pan oil is only 11. Copper ester is 52, and cashew nut shell is 41. Okay, so I have one question for you guys. Okay, why is the heating value of biodiesel is lower than that of diesel fuel? Anyone knows why is the heating value of biodiesel usually lesser than the diesel fuel? Anyone knows? Okay, nobody know, huh? Okay, it's okay. Because biodiesel actually contains oxygen, correct? Biodiesel contains oxygen, contains O, okay, oxygen. Okay, contains oxygen atoms. Okay, since the fuel contains oxygen it itself don't contains energy, correct? Okay, because oxygen cannot be burned to produce energy, correct? Okay, so the biodiesel has lower heating value. Okay, so here we show you the impact of the biodiesel on the efficiency of the SNGs. Okay, this biodiesel was produced by the from the waste cooking oil. So you can see here shows the diesel fuel, the pure diesel fuel, fossil diesel. And this one is 100% waste cooking oil. So you can see this biodiesel actually has a higher efficiency. Okay, has a higher efficiency, correct? Only B10 has similar efficiencies to the diesel fuel. B20, B15, and especially B100. Pure biodiesel actually has a higher efficiency than the diesel fuel. Okay, so next one is about biofuel on the major emissions. Okay, so this one again is produced from waste cooking oil. So we can see this one is HC4, the diesel fuel. So all the biodiesel generally has lower HC emissions because biodiesel contains oxygen. Okay, this biodiesel contains oxygen, can enhance the combustion process. And the CO emissions is smaller. Okay, again, it's the same reason. And the NOx emission, okay, so some of the fuel has a higher NOx emission, some of that has lower NOx emissions. Yeah, but generally it's quite similar. Okay, the next one I want to introduce the cashew biodiesel. It's the impact on the performance of IC engines. Okay, firstly is the BTE. Okay, so brake thermal efficiency. So basically, this cashew biodiesel has lower efficiency. Okay, has lower efficiency compared with the diesel, pure diesel fuel. So it's different from this with cooking oil, right? So from this case, actually, we can understand. Okay, different biodiesel because the properties is different. Physical properties, chemical properties is different. So its impact on the performance on the major emissions also will be different. Okay, you cannot say, okay, all the biodiesel has better performance or all the biodiesel has poor performance. Okay, it's not correct. And okay, so here shows the brake specific fuel consumption. Okay, so this biofuel has higher fuel consumption. Okay, this one is easy to understand. Okay, firstly, brake thermal efficiency is lower. Secondly, biodiesel contains oxygen, right? So heating value is smaller. Okay, since the heating value is smaller, to produce the same power, then you need to supply more fuel, correct? So it's very easy to understand. Okay, so next one is cashew biodiesel on the emissions of IC engines. So we can see actually CO emissions is higher than diesel fuel, and the HC emissions also is higher than the diesel fuel. NOx emission is lower. Okay, NOx emission is lower, and the smoke density also is higher for this kind of biodiesel. Okay, because this cashew nut shell actually is very has very high viscosity, and this one affects the fuel evaporation, affects the combustion process. As a result, okay, the performance is poor. So let me go back to here. So you can see this one is a cashew nut shell. Okay, biodiesel. So you can see this fuel has very high viscosity, correct? Okay, this one significantly affects the fuel evaporation, the fuel and air mixing process and combustion process. And also the heating value is very low, right? And the C10 number also is lower than diesel fuel. So all this affects the combustion process. As a result, okay, we can see the efficiency is lower than diesel fuel. The BSFC is higher than the diesel fuel, and the emissions also HCO, HC, and the smoke are higher than diesel fuel. Only NOx emission is lower. Okay, because of poor combustion process, the peak temperature will be lower. As a result, NOx emission will be lower. Okay. Okay, the next one we investigate is a copper biodiesel. Okay, on the performance of IC engines. Again, the first one is the BT. So again, this biodiesel actually has a better brake thermal efficiency than the diesel fuel, correct? And BSFC is higher than biodiesel than diesel. This also is reasonable because again, this copper biodiesel contains oxygen, correct? So this oxygen bring down the heating value. Since the heating value is smaller compared with the diesel fuel, so the fuel consumption will be higher to produce the same power, correct? So this one is reasonable. And again, okay, this one is its impact on the major emissions of SHs. Okay, for example, CO emissions, basically the CO emissions will be higher, and HC emissions also generally is higher than diesel fuel, and NOx emission is also a little bit high than the NOx emission, than the diesel fuel, and surface smoke density also is higher. Okay, so the carbon biodiesel actually also has it's a relatively higher efficiency, and but also has higher BSFC, the fuel consumption, and the CO, HC, and the smoke, all these emissions actually is poor than the diesel fuel. Okay, so next one is the pan oil. Okay, so pan oil actually is not converted into biodiesel because the pan oil actually is quite close to the diesel fuel already. For example, the heating value is 42 megajoules, correct, per kg. And diesel fuel is also 42 something, correct? It's quite similar. And the pan oil actually has a lower viscosity than diesel fuel. Okay, so you can see the brake thermal efficiency actually is higher for pan oil because the lower viscosity and can improve the combustion process. Okay, so the brake thermal efficiency is higher for pan oil. And the fuel consumption is lower because of the higher efficiency. The heating values are quite similar, quite close to each other, but the higher brake thermal efficiency means lesser fuel consumption, correct? Okay, so here's its impact on the major emissions like CO. CO emissions will be lower for pan oil, and the NOx emissions also is lower, and also smoke emissions is lower than diesel fuel. Okay, so next one I want to introduce the biodiesel is a different saturation level. Okay, saturation level. Okay, so so-called saturation level actually is defined as the percentage, okay, as a percentage of the saturated composition to the total, okay, to the total mass. Okay, for example, in this case, rapeseed biodiesel, we can see C16 Okay, this one is a saturated composition, and C18 again, this composition is saturated because there's no double bond. Okay, if the chemical contains double bond, then we see this composition. Okay, this chemical is not saturated. Okay, so here we can see the saturated composition is C16 C18 correct? So add together is 4.4, about 4.45. And C18 okay, this is one double bond in this chemical. And so there are two double bond and there are three double bond. Okay, this value 1, 2, 3 is the number of double bond in this molecule. Okay. So in the first two cases, 0 means there's no double bond, and this one also have no double bond, correct? So add together 4.45 is this is the sum of these two composition, correct? So divided by the total value, total mass. Okay, so equals to 4.45. So for the first case, rapeseed, okay, rapeseed biodiesel saturation level is 4.45 only. Sunflower, okay, the saturation level is this one plus this one divided by the total, okay, the sum of the total compositions, so equals to 9.54. Soybean biodiesel, okay, the saturation level is 15.2. Cottonseed is 29.7. So this is for different biodiesel. We can see the saturation level is different. Okay, so in this investigation, actually we hope to understand the impact of saturation level on the performance and on the major emissions of the engine. Okay, so here we show you the heat release of various biodiesel. So this one we can see is 10% engine conditions. Okay, this one is 50% engine conditions, and this one is 100% engine conditions. And so have 4 types of fuel biodiesel, just how I can mention. Okay, this one, this 4 types of biodiesel. So you can see rapeseed, okay, this is a black color, okay, it's a rapeseed biodiesel. So you can see rapeseed biodiesel actually has the highest or has the lowest saturation level, correct? So you can see the ignition delay time is the longest. Okay, this one is the longest, correct? The ignition delay time is the longest, correct? And this one has the lowest, okay, ignition delay time. Okay, so this one is the called the carbon seed. Okay, carbon seed. Okay, so from here, actually, you can see the with increase of saturation level, basically the ignition delay time will decrease. Okay, because because with the increase of saturation level, which means this percentage, okay, this is 2 components, the percentage will increase. Okay, this 2 composition don't have double bond, so it is easier break. The combustion process will be better, correct? So the higher saturation level usually has a better combustion process. Not always, okay, but generally, higher saturation level means a better combustion process. Okay, that's why the ignition delay time for the lowest saturation level fuel has the longest ignition delay time, correct? So at different timing is similar. Okay, at different timing, different engine mode is similar, correct? 10% engine mode, 50% engine mode, and 100% engine mode is quite similar. And also can see the peak heat release rate. Okay, the 10% engine mode has the lowest value. Okay, in the 50% engine mode has a medium moderate heat release rate, and the higher engine mode has a maximum heat release rate, correct? So here we show you the major emissions. Here's the major emissions of the 4 types of biodiesel. First one is the NOx emission. So you can see the rapeseed. The NOx emission has the lowest value at the 3 different engine conditions, correct? So has the lowest value. Okay, this one because just like I mentioned, rapeseed has the highest viscosity and also has the lowest saturation level. So the combustion process actually is the poorest in this 4 biodiesel. As a result, gas NOx emission will be lower, correct? Because of the poor combustion process, because of the lower temperature, peak temperature, so the NOx emission will be lower. However, okay, if compares the soot emissions, okay, the rapeseed biodiesel produce the highest soot emissions, okay, because again, this kind of fuel has the highest percentage over this kind of unsaturated compositions, okay. For example, rapeseed, we can see more than 95% contains double bond, right? More than 95% of compositions contains double bond. And the fuel contains double bond tends to produce more soot emissions. Yes, so we can introduce in the previous lectures as we introduce the molecular structures on the soot emissions. Okay, the next one I want to introduce is emulsion fuel with nano-organic additives. Okay, so here we show you 2 different emulsion fuel. The first one is an emulsion fuel by other researchers. So you can see this one is a milk color, correct? Okay, this one is a milk color, and the second one actually is tested by us. Okay, we collaborate with industry with companies produce emulsion fuel. So this the second fuel is conducted by us. So can compare the color. Okay, this one is a milk color. Okay, this one is more like transparent and similar to the color of diesel fuel, correct? Okay, so we can see actually in this in this emulsion fuel we have blended with MP9, MP15. Okay, this one is more like a surfactants. Okay, surfactants. And also had blend water inside in the emulsion fuel. Okay, the water percentage from 5% to 10% and until 50%, until 50%. Okay, and okay, the rice, okay, this one contains 90% of diesel fuel and 10% water. Okay, so we compare the physical properties and the chemical properties of the emulsion fuel. So this suppose with a diesel fuel for comparison, okay? And we can see the E5 has a heating value 40 megajoules per kg, and E10 has a heating value 38.25, E15 is 36.16. And this emulsion fuel by other researchers is 40.5 ohm. So we can see with the increase of water percentage, then the heating value will drop, correct? So this one is easy to understand because we know water cannot be burnt, right? So water don't produce any energy, correct? And so we also have organic additives in this emulsion fuel. For example, E5, we have 12.6% organic additives. Actually, it's some biodiesel. And also has some glycerin. And E10 contains about 11.5 additives, and E15 contains 10% of organic additives. Okay, so we can see the heating value with the increase of water percentage, the heating value will drop, correct? And the viscosity increase. Okay, the viscosity increase. Diesel fuel viscosity is 2.8. E5 is 8.8 and E10 is 10.6. E15 is 12.4. So the viscosity increase with the increase of water percentage and surfactants. Okay, the density, here shows the density E15 has a higher density. Okay, so my question for you guys, okay, why is the emulsion fuel has higher density than the diesel fuel? You can look at the major composition. Okay, why is the density of emulsion fuel has higher value than that of diesel fuel? Anyone knows?
Sir, because it is an emulsion. Diesel is completely liquid, but emulsion has some particles, other state.
Any more different opinions? Okay, you can look at this. Water. Okay, so what is the density of water? 1000 kg per cubic meters, correct? Diesel fuel is about 815 kg per cubic meters. So it's increase of water percentage. Okay, the density will increase because water has a higher density, correct? Okay, so with this emulsion fuel, actually we can improve basically we can improve the combustion process, and at the same time we can bring down the temperature, and thereby reduce the NOx emission, correct? So what is the working principle for the emulsion fuel? Anyone knows what is the principle for the emulsion fuel? Why the emulsion fuel can improve the combustion process, can reduce the peak temperature, and can reduce the NOx emission? Okay,
So,
so yeah, please.
sir, I think water is easier to heat, like in less temperature. Water
Mhm.
gets heated up and helps in increasing the temperature.
Okay, yeah, okay. Actually, we can see here shows the schematic. The water droplets is contained by the few droplets by the oil, correct? So once this fuel is injected into the engine under high pressure, high temperature conditions, okay, the water will absorb heat energy and then will evaporate. Okay, so during the evaporation, because the water is contained by the fuel, by the oil, correct? So when the water expands, then will expands become gas, then will explode. Okay, will explode. So by when the water droplets explode, so the oil surrounding the water droplets will be break. Okay, will be break into many smaller droplets. Correct. So by this way, we can see by this way, actually we can break the bigger droplets into bigger oil droplets into smaller oil droplets. So by this way, we can increase the surface area of the fuel, correct? And also can improve the fuel and mixing process. Okay, so this is a this is an explosion. We call the macro explosion. Macro explosion. Okay, so this is a macro explosion can improve the fuel and mixing process and increase the surface area. Okay, thereby also improve the fuel evaporation speed. So can produce a faster expansion speed, correct? Or evaporation speed, correct? Thereby can improve the combustion process. Okay, so by using the evaporation fuel, we had done the test in the engines, okay, in the four-cylinder engines. So here shows us the heat release rate. So you can see this is a diesel fuel. The first one is a diesel fuel. This is E5, E10, and E15, correct? So you can see the increase of water percentage. This ignition delay is become longer. Okay, why is the ignition delay become longer? Anyone knows? Anyone knows why with the increase of water percentage, the ignition delay time become longer? Nobody knows? Okay, it's okay. Because when the water evaporates, which means water will absorb heat energy, correct? Okay, will absorb heat energy. So which means we bring down the temperature in the combustion chamber, correct? We bring down the temperature in the combustion chamber. Okay, thereby when the temperature drop, then the ignition delay will become longer, correct? The combustion process will be affected because of lower temperature. So the ignition delay time will become longer, correct? Okay, and also the peak temperature also will drop. Okay, the peak temperature will also drop because the water absorb heat energy and thereby bring down the overall temperature. Okay. Okay, so here we can see the diesel fuel, the peak heat release rates actually is almost the same as E15, correct? But E5 and E10 actually has a higher heat release rate, okay? Higher heat release rate, which means that the combustion process actually is once ignited, the combustion process will be complete in a shorter duration, okay? In a shorter duration. Okay, which means once ignited, combustion process will be faster, but also the ignition delay time is longer. However, once ignited, okay, the combustion process will become faster, become short. Okay. This one again, you can use this one to explain because this is a macro explosion can promote the mixing between the air and fuel, and also can increase the fuel evaporation rate. Okay, so once ignited, combustion process will be faster. Okay, the second one is its impact on the breakdown efficiency. So this one black one is for diesel fuel, and this one is E5, and this one is E10, this one is E15. So can see compare the E10 and the diesel fuel. So for all the engine speed, we can see the efficiency has been increased. Okay, the efficiency has been increased, especially in this region. Okay, in this position, the efficiency has been increased by 14.2%. Okay, so a huge improvement. Because we know for the modern engines, okay, so designed perfectly, correct? So even you want to increase by 2%, 3%, yes, might be very challenging. However, in this case, actually, by using the immersion fuel, the best one, we can improve the efficiency by 14.2%. Okay, even at this position, the lowest improvement, we still can achieve 6% improvement in the efficiency. Okay. Okay, so next one is the NOx emission. Okay, so NOx emission has been significantly reduced. This is a diesel fuel, E5, E10, and the E15. So you can see the E15 has the biggest reduction, right? Okay, so this one is again easy to understand because the water, E15 contains 50% water, and the water will evaporation will absorb a lot of heat energy, thereby bring down the temperature, bring down the peak temperature, correct? As a result, okay, the thermal NOx emission will be the minimum, will be reduced, correct? Okay, so next one is the CO emissions. Okay, so CO emissions is basically higher for immersion fuel. Again, because of the lower temperature, it is not favorable for the oxidation for CO, correct? But the absolute value is still small. For example, the maximum is 200 ppm. And actually at higher engine load conditions, okay, from medium engine load to high engine load conditions, actually CO emissions is similar, it's quite similar to each other. Only at partial load conditions, okay, only at very low engine load conditions, yes, the CO emissions is higher for immersion fuel because of the reduced temperature. Okay, and also had measured the smoke emissions. I didn't show the figure here. Also, but we have done another test. Okay, so the smoke emissions can be reduced by up to 70%. Okay, can reduce by up to 70%. Okay, so that's the end of this lecture. Okay, so we still have 6 minutes left. Yeah, so maybe we can use this time to answer some questions. Okay. Yeah, also, if any issues you hope to discuss with me, also can we're happy to do so. So, any questions?
So any question from the participant side? So, sir, the micro explosion, what you told about the emulsified fuel, we can also tell it as a secondary atomization, right, sir?
Yeah.
Secondary atomization.
Yes. Yes. Correct.
Because it proceeds through the after the first atomization through nozzle, it breaks down the latter part of the emulsion process. So what is the stability condition of those types of emulsion you observed?
Oh, okay. Stability, you mean the duration or?
Yeah, the duration the emulsions can self-sustain
Oh,
for.
okay. Sure. Okay. Usually for this kind of immersion fuel, okay, can only keep stable for a few days. Okay. Yeah, especially if just use mechanical methods to produce immersion fuel, can only sustain maybe a few hours. Okay, 2 hours, 3 hours. If you use surfactants, okay, surfactants, then maybe you can keep stable for 3 days, okay, up to 3 days. However, okay, for this kind of emulsion fuel, actually we keep the emulsion fuel in the label for 6 months. Okay, for 6 months, even after 6 months, we didn't notice any obvious separation. So it's very stable.
Sir, for surfactants, what was the hydrophilic lipophilic balance HLV value for those combination of surfactants you have used?
Okay, so for for our emulsion fuel, we use MP9, MP15. Okay, these are two of the surfactants used in this emulsion fuel. And but some other, others they use different surfactants. Okay, there are some common surfactants. I cannot remember the name. Yeah, but you can Google. You can easily find out. Okay, which are commonly used surfactants. So we had different surfactants, and the properties will be different. Okay, this one is more like a nanoparticles. Okay, nanoparticles. That's why the emulsion fuel produced by this biofuel and by the fossil fuel, and also the surfactants can look transparent because it's a nanoparticles. Okay, it's very small, very tiny. So it's more like has the properties of transparency.
Is there any, sir, plan of using the emulsified fuel with gaseous fuel like hydrogen, CNG, LPG, those type of thing combination? How it works?
Oh, okay. You mean for the gas engine, huh? Yeah, of course, this one can use as the panel fuel. Okay, for the gas engines, if pure gas engines, of course, not necessary because we just use the pure gas, correct? Natural gas, LPG, and other types of gas. Okay, so for that application, definitely you don't need to use emulsion fuel or use any liquid fuel, correct? However, okay, if you use so-called dual fuel combustion
Yes.
modes, yeah, then dual fuel, yeah. So emulsion fuel can be used as a panel fuel, correct?
Yeah.
For example, RCC engines and other dual fuel engines. Okay, actually dual fuel engines commonly used in marine engine already, correct? So we can use emulsion fuel as the panel fuel. Okay, so usually it's a panel fuel is only inject by maybe 5%, 10%. Okay, maximum maybe 20%. Correct. Most of the fuel is still natural gas, LPG, LNG. Correct.
Okay, sir. Okay. So, participants, do you have any query to ask?
Okay, if no question, we'll stop here. See you afternoon. Yeah, so we're going to show you the very special one. Okay, this afternoon. Okay.